since I have oxygen in the carbon dioxide and the water, I have to account for both of those. So the way I'm going to do that is by adding and knowing that each time I change one of them, I'm going to have to do a new addition to see how it was infected. So I have 2 oxygens in the carbon dioxide. I have 1 in the water, 3 total right now. And so we can see that from a conservation standpoint, this equation is a mess. None of the elements are balanced. But there are a couple of things that we can do. First of all, if you remember one of the tips from last time, it was if we have a compound that has multiple subscripts, those subscripts usually play a role in the balancing of the equation on the other side. And so what I'm going to do is I'm going to make this a 4 and this a 10 based upon those subscripts. Now, those may not be the final numbers, but they might provide us a little bit more clarity in terms of what to do next. And that's really important for us. So if we do that, I now have 4 carbons, because 4 times 1 carbon in carbon dioxide is 4. I now have 20 hydrogens. And I now have 4 times 2 is 8. 10 times 1 is 10. 18 oxygens in total. So this hasn't really made things super better, but it's at least made things a little bit more clear. From this vantage point, I know that my carbons are balanced in this ratio. 1 butane for every 4 carbon dioxides. I also know that my relationship between water and butane is going to be 2 to 1. It's not going to be even. So to balance this out, I've got the carbons figured out, at least for the moment. To balance out the hydrogens, I'm going to need 2 butanes. Those 2 butanes are going to mean I have 8 carbons and 20 hydrogens. Changing the butane means I'm going to need to change the carbon dioxide as well. To give me 8 carbons, I'm going to need 8 carbon dioxides. And that's going to change my oxygen count as well. 8 times 2 is 16. 10 times 1 is still 10. 26 oxygens in total. So all of the steps that we've done thus far, we now have carbon and hydrogen balanced. And we now have a position where we can balance oxygen as well, because I have 26 over here on the product, and every oxygen atom comes in pairs on the reactant side. So I need 13 pairs of oxygens. 13 times 2 gives me the 26 that I'm supposed to have. This type of reaction is called a combustion reaction. Combustion reactions we can pick out as having a reaction between some kind of a substance and oxygen, creating oxide compounds. Most common of these are carbon dioxide and water. Now, those products are the result directly when we burn hydrocarbons, organic materials that have carbon and hydrogen in them. So when we burn wood for a bonfire, carbon and hydrogen are part of the wood. They're part of the cellulosic structure of that wood. And we get carbon dioxide and water as a result of those burning. These are the most difficult to balance, though. And it's because of this factor right here. So if we had not done my subscript trick, let's just clear the board here and go after it again. If we had done this straight up without the subscript trick to kind of guide us, we would have ended up in a spot where if we were following our other guidelines, we have looked at this and said, okay, balance the carbon first. I need 4 carbon dioxides. That gives me 4 of those. Balance the hydrogens next because there's only one place where hydrogens are. I need 5 of those. That'll give me 10. Oxygens now, I have 4 times 2 is 8, plus 5 more, 13. And I would have got to a spot where I have an odd number of atoms that can only be balanced by an even number of atoms. Something that is not technically possible to do. If you find yourself in a situation like this, and again, combustion reactions are the most common place where we see this. It does happen in other places as well. But if you find yourself in this position where you have something that is seemingly unbalanceable, the correct course of action is to double everything other than the thing that you're trying to find. So if I double everything, this turns into a 2. This becomes an 8. This becomes a 10. And I recalculate. Now I've got 2 even numbers to balance. That's where the 13 can come in. As I said, if you find yourself in this particular spot where you're trying to balance an odd number with an even number, and you find you can't do it, double everything other than what you're looking for. That'll turn that odd number into an even number, and you should be able to solve it from there. All right. Questions about this problem? All right, let's do another example, an easier example. This is an example where we see the idea of clustering come into play. I can see that on both sides of this equation, I have SO4. SO4, as you know, is the sulfate ion. And so I've got potassium, I've got sulfate, I've got barium, I've got chlorine. Now, one of the most common mistakes that students make is that they assume that if we have a subscript of some kind, then that's what we need to track and keep it clustered together. That's not what I mean when I say keep the clusters together. If it's a cluster, it's going to appear in the same manner on both sides of the equation. And we usually have names for those clusters. They're usually polyatomic ions that hopefully we're starting to grow into recognizing overall. So if I look on each side, I've got 2 potassiums and 1 sulfate, 1 barium, and 2 chlorides. On the product side, I have 1 potassium, 1 sulfate, 1 barium, 1 chloride. Now, what I want you to pay attention to here is that there's some commonality here. So the barium and the sulfate are already balanced as is. The potassium and the chloride are not, but notice that they're off by the same amount. And notice that on the side in which they are off, they are in the same compound. This is not a mere coincidence. This is actually an attribute of a type of reaction called a replacement reaction. Replacement reactions are best recognized for their clustering because of their ion capability, and because oftentimes we will see this kind of a phenomenon occurring where we do some balancing and then all of a sudden we can see very clearly the end of the road, the last step. Because since these are both 2s and these are both 1s, adding that coefficient of 2 will solve both simultaneously. These ones tend to be very easy to balance as a result. All right. Any questions with this example? All right, it's your turn. Chances are not very good that you'll be able to work together, but what I want you to try to do is I'm going to give you, let's say, a good 10 minutes. For those of you that are here, I'll answer some questions for you individually. But in that 10 minutes, try to balance these 3 equations. Keep in mind the things that we looked at and some of those guiding principles that we use. So go ahead and work on those. We'll come back in about 10 minutes with the answers, and we'll try to catch any questions along the way. All right, so this first one, this is one of those occasions where the move over the subscripts to coefficients doesn't really work out so well. It actually kind of gets things confused. What you can do though is if we look at it, I've got carbon, hydrogen, and oxygen. I've got 5 carbons, 12 hydrogens, and 2 oxygens, 1 carbon, 2 hydrogens, and 3 oxygens in total. From here, we can handle it relatively straightforward. I have 5 carbons. I'm going to need 5 carbon dioxides to balance that out. That's going to turn my 1 carbon into 5. I'm now balanced on carbon. For the hydrogen, we're going to need 6 waters to give me the 12 hydrogens to match. And so now I do my math again on the oxygen. I've got 10 from carbon dioxide, 6 from water, for a total of 16. Now, unlike the example that I did, the first one, this is not an odd-even mismatch. 16's an even number, 2's an even number. They're both even. So I don't need to double everything like I did here. I can just balance it directly. 8 sets of 2 would give me 16, and that would balance out everything. So the double everything method only is necessary if I have an odd number on one side and an even number on the other. If they're both even, then they should balance each other out without doing anything extra. In the second example, I've got nitrogen and oxygen on each side, 2 nitrogen, 2 oxygen on the reactants, 2 nitrogen, and 3 oxygen on the product side. This is another one of those examples. This is, I've got an odd number here and an even number here. Rule of thumb, double everything other than the element that you're trying to balance. So that means I'm going to need 2 of the nitrogens, 2 of the N2O3s. That means I'm going to get 4 of these, 4 of these, and this is now 6. And now I can see that all that was necessary, all that was left, is a 3 there in front of the oxygen. Just as a word of note, you could have gotten to the same place. Notice that this is an occasion where the subscripts did turn into coefficients on the other side. You could have balanced it that way as well. In a similar fashion, I've got a gold sulfide, so I've got gold, sulfur, and hydrogen, gold, sulfur, and hydrogen, 2, 3, 2 on the reactant side, 1, 1, 2 on the product side. If we follow our coefficient subscript kind of relationship, a 2 from the gold and a 3 from the sulfur, change our outlook on the product side. I now have 2 golds, 3 sulfurs, and 6 hydrogens. Gold and sulfur are now even. Hydrogen's the only one that is not. A 3 there fixes that. Any questions about these 3 examples? Okay, so That completes for us the first 3 sections out of Chapter 5. That also happens to be the subject of your post-lecture that is due over the weekend. Now, moving on into Section 4. Section 4 regards the prediction of chemical reactions. And in particular, what we're really going after here is, can we identify a chemical reaction by its type? And then can we use that chemical reaction and use that reaction type to kind of predict what the products of a reaction would be if I just gave us a couple of reactants? And that's what your lab was going after this week as well. A lot of the study questions out of that lab were kind of open-ended. What happens if I have potassium and react it with water? What happens if I take magnesium and react it with oxygen? Those were the kinds of things that you had to learn how to predict in lab. Understanding these 5 chemical reaction types goes a long way toward helping you do that. And so we're going to go through each one of these in some more significant detail and give you some things to look at, some things to look for along the way to make sure that you're kind of on the right track. So our 5 types of reactions are these. Combination. Combination is sometimes also referred to as synthesis. So don't be surprised if you see either one of those used for the first reaction type. Decomposition reactions. Reactions where stuff decomposes, breaks down into smaller pieces. Replacement reactions. Replacement reactions are identified based on the number of compounds involved. So a single replacement reaction has 1 compound involved as a reactant. A double replacement reaction has 2 compounds involved as reactants. That's the difference between them. And then finally, combustion reactions, which we spent a little bit of time talking about today already. So let's take a look at each one of these in a little bit greater depth. Let's start with combination reactions. Combination reactions occur when we have small elements or compounds reacting with each other to make a single product. Now, the composition of those multiple reactants can vary. They can be elements. So for example, if I have zinc, metallic zinc, reacting with molecular chloride, or chlorine rather, they together can make the compound zinc chloride. In that case, I have 2 elements reacting with each other to make an ionic compound. It can also happen where I have an element and a compound reacting. In this case, on the bottom, I have hydrogen gas reacting with carbon monoxide gas to make an organic compound here, formaldehyde. But even at that, we are not limited solely to reactions involving elements. There is also the possibility of reactions like these. where I've got multiple compounds. And here I've got dinitrogen pentoxide, N2O5, reacting with water to make nitric acid. In the end, it is two compounds coming together to make one new product. Two compounds as reactants coming together to make one compound as product. One place where we can tend to get confused in the identification of chemical reactions, do not pay any attention to the coefficients. When we say that we have a single product, we're not referring to the coefficient, we're referring to the fact that there is only one chemical formula on that product side of the reaction. So I've got multiple reactants over here. I've got one product on the other side. That's a combination reaction, also known as synthesis. Now, combination reactions have an analog known as decomposition reactions. Decomposition reactions are essentially the opposite of a combination reaction. In a decomposition reaction, we have one reactant turning into multiple products. And this can come in a variety of different forms as well. The compounds in question can be very simple compounds, like this ionic compound, mercury 2 oxide, breaking down to form mercury and oxygen. You've also seen the example in lab of water breaking down into hydrogen gas and oxygen gas with a little bit of help from electricity. Decomposition reactions can even be more complex than this. Here we have an example of hydrogen peroxide breaking down into water and oxygen. And once again, don't get caught up in the coefficients here. Get caught up in the number of products. Here I have one reactant. Here I have two products. So we're fitting into that general mold of decomposition reactions. One reactant generating multiple products. And here is where I'm going to stop for today. The next type of reaction, replacement reactions, they're best mentioned together, single replacement and double replacement. We don't have time to do both. We maybe would get through single and it'd be kind of a hurry to do so. So we're going to stop there. So Monday's virtual section, we are going to be doing the rest of this chapter. And the rest of this chapter is going to focus in on replacement reactions and identifying markers, predicting precipitates, and other kinds of ways of showing that a chemical reaction is taking place in those kinds of replacement reactions. Because replacement reactions on an equation page can be a little bit misleading when we get to the laboratory. Not everything that should happen according to the equation actually happens in the lab. And what we'll get into on Monday is why that is the case. So we'll pick it up from there. Have a good weekend. I'll see you virtually on Monday.